Welcome, Java developers and IT enthusiasts, to a deep dive into the future of coding. Today, we're tackling a challenge as old as software itself: performance. We all know that feeling, a Java application that starts to chug, consuming more resources than it should, impacting user experience, and driving up cloud costs. Whether it's an enterprise-grade backend, a high-throughput microservice, or a complex data processing engine, inefficient Java code can be a silent performance killer. Traditionally, optimizing code has been a painstaking, manual process, requiring seasoned expertise and countless hours of profiling and refactoring. But what if there was a way to accelerate this, to make our Java applications inherently more streamlined and resource-effective? Get ready to explore a paradigm shift: the application of generative AI for Java code optimization. Imagine having an intelligent assistant that not only understands your code but can also suggest significant enhancements, guiding you towards more efficient, readable, and performant solutions. This isn't just about minor tweaks, it's about fundamentally refining existing Java codebases to unlock new levels of speed and efficiency. In this video, we'll demystify how generative AI can serve as your ultimate co-pilot, transforming the way we write and maintain high-performance Java applications. Stay tuned, because the way you optimize Java is about to change forever. So, why is optimizing Java code such a critical endeavor? In today's interconnected world, every millisecond counts. Slow applications frustrate users, leading to abandoned carts, lost productivity, and damaged reputations. Beyond user experience, inefficient code directly impacts your bottom line. Higher CPU and memory usage translate to increased infrastructure costs, especially in cloud-native environments where you pay for what you consume. A poorly optimized Java application might require more powerful servers or more instances, unnecessarily inflating your operational expenses. Furthermore, in competitive markets, superior performance can be a significant differentiator, allowing your applications to handle more concurrent users or process larger datasets without breaking a sweat. It's not just about making things faster, it's about building more sustainable, scalable, and cost-effective systems that can adapt to ever-growing demands. Ignoring performance is akin to leaving money on the table and opening the door to a subpar user experience. Historically, achieving peak Java performance has been a heroic, often solitary, effort. Developers spend countless hours with profilers, meticulously sifting through call stacks, identifying bottlenecks, and then painstakingly rewriting sections of code. This process is inherently reactive and fraught with challenges. It requires deep knowledge of JVM internals, concurrency models, data structures, and algorithmic complexities. Even for experienced engineers, optimizing complex codebases can be like finding a needle in a haystack, made more difficult by tight deadlines and the ever-present risk of introducing new bugs during refactoring. It's a labor-intensive, time-consuming task that often consumes valuable developer cycles that could otherwise be spent on new feature development or innovation. The manual nature of this work means that many potential optimizations are simply left unexplored due to resource constraints or lack of specialized expertise within a team. We need a better way. This is where generative AI steps onto the stage, not as a replacement for developers, but as an incredibly powerful accelerator. At its core, generative AI, exemplified by large language models, LLMs, is designed to learn patterns and structures from vast amounts of data, in our case, millions upon millions of lines of code. Armed with this understanding, it can then generate new content, suggest modifications, or even translate between different coding paradigms. When applied to software development, generative AI tools can analyze existing code, identify common anti-patterns or suboptimal constructs, and then propose more efficient alternatives. Think of it as having access to the collective wisdom of thousands of expert Java developers, distilled and made available at your fingertips. It moves beyond simple syntax highlighting or auto-completion, it's about intelligent code understanding and transformation, revolutionizing the way we approach optimization. Imagine an AI copilot sitting right beside you, constantly scanning your Java codebase. This isn't some far-off sci-fi fantasy, it's rapidly becoming a reality. Generative AI tools can act as an intelligent assistant, pinpointing sections of your code that could benefit from optimization. They go beyond simple linting, they understand the semantic intent of your code. For instance, an AI might recognize an inefficient loop structure, a suboptimal use of data collections, or a repetitive pattern that could be streamlined. It can then suggest refactorings using more modern Java features, propose alternative algorithms, or even flag potential concurrency issues before they become production nightmares. This immediate, context-aware feedback loop empowers developers to make informed optimization decisions early in the development cycle, significantly reducing the debugging and performance tuning efforts later on. It's about being proactive rather than reactive, making every line of code count. To illustrate this powerful concept, let's consider a common Java task: processing a list of strings. Our original code analyzer class, which mirrors a typical real-world scenario, tackles this problem using traditional imperative loops. It iterates through a list, filters strings based on length, converts them to uppercase, and then sums their lengths. While perfectly functional, this approach often involves multiple iterations, temporary data structures, and explicit conditional checks. It's verbose, can be harder to read at a glance, and sometimes less performant, especially with large datasets, due to the overhead of intermediate collections and the sequential nature of explicit looping. This kind of code is prevalent in many existing Java applications, written perhaps before modern Java features were widely adopted, or simply due to habit. It's a prime candidate for AI-driven refinement, demonstrating where an intelligent assistant could step in and suggest a more elegant solution. Now, let's look at the transformation. The AI-optimized code analyzer class accomplishes the exact same task, filtering, transforming, and summing string lengths, but does so using Java's powerful Streams API. This version is a prime example of the kind of optimization a generative AI might suggest. Instead of explicit loops and temporary lists, we have a fluent, declarative chain of operations: stream.filter, .map, .map to long, .sum. This not only makes the code significantly more concise and readable, expressing the what rather than the how, but it also inherently lends itself to potential performance benefits. The Streams API is designed to be highly optimized, and its operations can often be executed more efficiently, sometimes even in parallel, by the Java virtual machine. This shift from an imperative, step-by-step approach to a functional, declarative style is a common recommendation for modern Java development, and it's exactly the kind of intelligent refactoring an AI can identify and propose with remarkable speed and accuracy. But a suggestion is just a suggestion until it proves its worth. This is where empirical validation comes in. Our provided code includes a performance tester that doesn't just show you the before and after code. It actually runs both versions against a large, identical dataset and measures their execution times. This critical step demonstrates the tangible benefits of AI-driven optimization. You'll observe a clear comparison of how many milliseconds each approach takes to process a million strings. In many cases, you'll see a significant reduction in execution time for the AI-optimized, streams-based approach. This isn't theoretical, it's a measurable improvement that directly translates to faster application response times, lower resource consumption, and enhanced scalability in real-world scenarios. The performance tester provides that concrete evidence, showing that these AI-suggested refactorings aren't just about cleaner code, but genuinely faster code. The impact of generative AI extends far beyond simply converting loops to streams. Imagine an AI analyzing your application's data flow and suggesting a more efficient data structure, perhaps replacing an array list with a linked list where removals are frequent, or recommending